In this video, we're going to take a look at section 2.2 on graphs. So in this section, we're going to focus on this particular method for graphing, which we haven't technically used in the course yet. So we've done some graphing already. We graphed circles in section 1.3. We graphed lines in section 1.4. But the methods we used to graph those equations were really shortcuts, even as difficult as they might have been. And we were able to do that because we knew something about the graphs ahead of time. So we knew this is this type of equation, and we know that the graph will have this kind of shape. And we were able to use that to our advantage to find, we were able to more efficiently graph, right? We knew what we needed to, the minimum that we needed to get the shape that we were supposed to get. So for example, graphing a line, you need 2 points, right? We know the shape is a line. We know for that you only need 2 points. What's the quickest way we can find 2 points? For a circle, we knew the center was important, and then the radius told us how far out to go from that. And so we just quickly put that graph together using just the necessary information. But that isn't always possible. There are lots of other kinds of graphs, and you may not always recognize the type of graph that you're dealing with, right? The equation may not give away that the shape of this graph is going to be blank, right? We might not know that ahead of time. And so if we don't know that ahead of time, we don't know what shape to expect, then there's no shortcuts. And so today we're going to learn a method for graphing that, while it's not the most efficient method, it is powerful in that it always works. And I call it the generic method. I got that from a supervisor that I had as a graduate student. That was his name for this particular method because it doesn't really have a name, but it's kind of nice to be able to refer to it in some way. So the generic method for graphing: find a handful of solutions to your equation. And we'll talk about that process in just a second. Then plot those solutions as points on the Cartesian coordinate system and look for a pattern. Once you've established what the pattern is, connect the points according to that pattern. So really what we're doing here is inductive reasoning. So you know about deductive reasoning from like Sherlock Holmes, right? So deductive is, given this broad, set of observations, we can narrow it down to a specific conclusion. So that's, deductive is starting from the general and moving toward the specific. Inductive reasoning is the reverse of that. It's starting with the specific and then generalizing. Maybe I shouldn't use the word generalizing there. It's moving from the specific to the general. So you take specific clues and then generalize those to get a broader truth, right? And that's what we're doing with the generic method for graphing. The solutions we're finding are the specifics. They are specific solutions to the equation. From those specific ones that we find, we will generalize where we think the rest of the solutions are located based on the pattern that we see emerging. So that is the method that we want to use. It's powerful because that works on any kind of equation. We can use this method to graph circles and to graph lines and to graph parabolas and to graph whatever two variable equation we might be given. The drawback is there's really no shortcuts here, and so you might have to find, and I'm being vague on purpose, right? Handful of solutions. How many is that? It really kind of depends. It depends on how complicated the pattern is, and it depends on how well you choose those solutions. And so if you choose them poorly, which you might not know ahead of time, you might not be doing it on purpose. It's not anything that you're doing wrong. It just can be a matter of luck, right? You might choose them poorly for whatever reason, and you don't get a good sense of the pattern, so you have to find more solutions. So steps 1 and 2 are repeated as necessary until step 3 is accomplished, until a pattern emerges. And sometimes it can take a while. I would say 4 points minimum for a handful of solutions. Find 4, but you might need more than that for some situations. The other thing I like to point out is that graphing calculators graph by this method. So when you type an equation into a graphing calculator, it doesn't it doesn't analyze it and say, oh, this is a linear equation. That means it's just a line. I just have to find 2 points. It's not that smart, right? What it does is it takes your equation, finds hundreds of solutions, not just a handful. It's a computer, so this thing it can do really well, right? It can find hundreds of solutions really quickly, plots them all as points. And again, it's not smart enough to look for a pattern. It just connects the points with little tiny straight lines. So when you zoom out, there's a curve to it. But if you zoom in, you'll notice it's choppy, it's blocky, because it's taking these solutions and just drawing little lines between all the itty bitty solutions it has all the way through the graph, right? I say itty bitty solutions. That doesn't make sense. I don't know why I said that. But the lines are itty bitty because the solutions are close together. That's kind of what I was trying to say. But there's hundreds of solutions really, really close together. And there's little tiny lines connecting those solutions. So anyways, let's practice using this method. So now for step 1, it says to find a handful of solutions. And sometimes students don't know how to do that. How do I take an equation with 2 variables and find a solution to it? You pick a value for one of the variables. Now, generally, we like to choose the value for x, plug that into the equation, and then let the equation tell us the value for y. But you don't have to do it that way. You can choose a value for y, plug that into the equation, and then let the equation tell you the value for x. But so either way works. You pick one, plug it into the equation has to tell you the other one. So you get to choose one, and then the equation determines what the other value has to be. You take those 2 numbers, put them together as an ordered pair, and that gives you a solution, which can then be marked on the Cartesian coordinate system as a point. Right? And you have to do that a handful of times. So you'll have to go pick a different number for x, plug it in, get another number for y. Pick a different value for x. So do that 3 or 4 times to get 3 or 4 solutions, plot those as points. Hopefully you'll know what the pattern is from that. If not, find a few more solutions and plot those points. And what's nice about having to go back is you just fill in the gaps, right? So if you have part of the pattern in one spot, but it's unclear what's happening in another spot, choose values of x in that particular spot. And that should fill in that detail for you. And then from there, hopefully you'll be able to figure out the graph. All right. So graph this relation. It actually turns out to be a function, but either way, determine the domain and range. Now we talked about domain and range in section 2.1. It'll be easier in this section because we won't have to determine the domain and range from the equation. We're going to determine it from the graph, and I think you'll find that's an easier exercise. And I just gave away the answer already to the last part. Determine whether the relation is a function, and I already said yes it is, but we will see from the graph. That's probably the easiest way to tell. Draw the graph first, and then if it passes the vertical line test, it's a function. Again, all things we talked about in 2.1. All right, so finding a handful of solutions, you probably recognize the way of organizing that information as a table. So when I set this up, you're going to be like, oh, that's what he's talking about. Right, so we set up a table like this, 1 column for x, 1 column for y, and to find a solution, I pick a number for x, I plug it into the equation, and then let the equation tell me what I should put here for y. So I'm going to pick x equals 1. So that was my choice. I could pick any value for x I wanted. There's limitations there, but in theory, you can try anything you want there. Y equals the square root of 1 minus 6. The square root of 1 is 1. 1 minus 6 will be negative 5. And so I get y is equal to negative 5. So that's what I put in the table. And that gives me, I didn't really leave myself very much room to write this, but that gives me the solution 1 comma negative 5, which I can then mark as a point on the Cartesian coordinate system. Right? Which I can wait, but I'll just go ahead and do that now. We have x, we have y, so we have 1 comma negative 5. 1, 2, 3, 4, 5. And I'm going to do one more, and you'll see why in a few minutes. All right, so this is 1 comma negative 5, which is right here. Of course, 1 point does not make a pattern, right? 1 point's not going to tell you anything about what this graph looks like. 2 points is not really enough information because with 2 points, that will always look like a straight line, right? With just 2 points. And that isn't going to be the case here. So one thing that really drives me crazy, so if you're one of my students and you want to drive me crazy on the test, if you want to throw away a few points to do that, is when students draw every graph like it's a line. That drives me bonkers, right? So linear equations look like this: y equals mx plus b. If it doesn't have that structure to it, the graph will not be a line. The only time a graph is a line is if it looks like this, right? Or ax plus by equals c, right? That's the other way it could be written. But if it's not a linear equation, the graph isn't a line. So anything else happening with the x, if there's a square root, absolute value, raised to the second power, or on the y, if any of that stuff happening to the y, the graph will not be a straight line. But I feel like some students I have, their perception of graphs is that the graphs are just lines. That's what they think of when they think of graphs, is it's always a line. And I'll see that on every one of their answers. Like, no matter what the equation looks like, the graph always comes out as a line on their paper. And that is a perception you want to change if you have that perception. When I say graph, you shouldn't think line. That isn't always the case, right? We've already saw that in chapter 1, right? Graphing circles, right? Sometimes the graph can be a circle. In this case, it's going to be like a sideways parabola, right? But it's not going to be a straight line. So don't make that assumption. All right, so what I would like you to do is pause the video and you find another solution to this equation. All right, and then resume the video and I'll write a few more on here. And maybe one of the ones I write down will be one of the solutions that you came up with. Okay, so I'm not going to show the work for all of the solutions I have written down here. And I'm sorry, when I was saying pause the video and do some solutions, I was about to hesitate because I was like, maybe there's one other thing I should say. But I thought I'll just kind of let you do that on your own if you followed through with my suggestion. And that is, while you in theory could pick any number you want for x, there's some numbers that aren't going to either work out very well or are not going to work out at all. And so I thought about maybe warning you about, be careful what you choose for x, try to pick these kind of numbers, but I thought I'll let you go on your own, and maybe you'll discover that you got to be careful what you choose for x. So maybe you were thinking, well, if I picked x equals 1, maybe you thought I'll pick x equals 2. And if you pick 2 for x, that actually isn't an incorrect choice, but it also isn't the best choice either. So if you pick x equals 2 and you plug that in for x, you get the square root of 2 minus 6, but the square root of 2 doesn't simplify. And so you'd have to plug that into your calculator. It's going to be a decimal. It's going to be a run-on decimal, which makes it more difficult to graph. It's a headache to deal with. So when you're choosing your values for x, you want to pick numbers that will work out nice in the equation if possible. 2 doesn't work out nice. So again, it's not wrong to choose that value, but it's also not the easiest thing to work with. What works nice with square roots? That's the kind of numbers you want to pick for x, are numbers that you can take the square root of, so it works out nice. Your next best choice would have been 4. So choose 4 for x, plug that into the equation. Square root of 4 gives you 2, right? It simplifies nicely, and then 2 minus 6 gives you negative 4. And so you get the 0.4 comma negative 4. But other good choices would have been 9, 16, 25. Now, the numbers start to get kind of big where you might not fit it in your graph very well. So also keep that in mind, that while 25 is not a bad choice at all, it might not be an easy number to graph. It's, the number's kind of large. But if you choose 9, you get negative 3 for y. If you choose 16, you get negative 2 for y. If you chose 25, you get negative 1 for y. And one that many students will avoid because they're just not comfortable with it is choosing 0 in this case. But 0 works in a square root. You get the square root of 0 minus 6. That'll be 0. Square root of 0 is 0. 0 minus 6 will be negative 6. And so I get 0 comma negative 6, which not only is an easy one to get, but really is a critical point for this graph, because that's as far to the left as you can go with this graph. I can't choose any lower values for x. If I tried to choose like negative 1, for example, I get y equals the square root of negative 1 minus 6, but we already talked about square root of negative numbers is going to be imaginary. And imaginary numbers have no home in these kind of graphs, right? The x-axis is a real number line. The y-axis is a real number line. We do not have a place to graph imaginary numbers, so that just has to be avoided. So -1 doesn't even work. 0 is as low as you're going to go with this equation. And so that's a really important point to find, because if that's the lowest value you can choose for x, that's the point that's furthest to the left in your graph. And you want to know where that's located. So, so we have 4. Let me go ahead and mark these points. So we have these handful of solutions. Now we're going to move on to the next step, plot them as points. So 4. And I'm going to try to fit 9. Let's see, 5, 6, 7, 8, 9. Not really the best, but I think it'll work. I don't know. The thing about drawing these by hand is, especially with this kind of equation, is it might not look the way it's supposed to. So let's just see what happens. So I have 1, -5. This is -4 here. So 4, -4 would be about right here. 9, -3 would be way down here. And yeah, it kind of has a little arc to it. The problem, one of the problems is, like, I left a big gap here, and then the rest of the gaps are smaller. That's going to make my graph not look quite the way it's supposed to. And then I'm not going to graph the 16, but then 0, -6 is a really important point to graph, which is right here. And you'll notice there's a little bit of a bend to this. So it's not a straight line. It shouldn't look like a straight line. That's the thing is, you know, depending on the points you find, your mind might think of it as a straight line, or if you're drawing it by hand, it might kind of look like a straight line, but I know it shouldn't be. And so I should plot points until I'm sure that I see why it's not a straight line, because the graph shouldn't look that way. And so it's going to look something like this. Right? It's going to have sort of an arc to it and kind of level out as it goes to the right. So this is not the best drawing of this graph I've done, but serviceable. So that's what the graph looks like. And it stops right there. So it just dead ends at that point 0, -6. It doesn't go any further to the left and doesn't go any further down. So this is the graph for that equation. And that's how you find that graph using the generic method. For the domain and range, remember the domain are all the possible values that x can equal. On a graph, the x-axis runs left to right. So a really convenient way of finding the domain once you've drawn the graph is to ask yourself, how far to the left does the graph go and how far to the right does it go? And that will give you a sense of what the domain is. That will tell you how the smallest numbers you could choose for x and the largest numbers you could choose for x. And so this graph, how far to the left does it go? It goes as far to the left as this point, which is 0 on the x-axis. So the lowest value I have for x is 0. How far to the right does it go? It goes forever to the right, so it's going to go to infinity. And those are all the different possible values for x, everything between 0 and infinity. For the range, same idea. It's what is it possible for y to equal. The y-axis is vertical. It runs up and down. So to find the range, you ask yourself a very similar question, except you change to the vertical direction. And while it's, left to right is like if you're going to mention both directions, usually we say left and then we say right. For the vertical direction, normally we'd say up and down. That sounds the more common way to say those directions together. But for the range, because you're going to write it as an interval, you want to start with the smallest number first and the largest number second. And so you actually want to go the other way. How far down does it go? You want to consider that first, and then how far up does it go? So how far down, how far up? This graph, how low does it go? This point here is the lowest point on the graph, and you want the y coordinate for that point. So -6 is the lowest y value on the graph. How far up does it go? Well, if you follow this pattern, it's mostly going to the right as it heads in that direction, but it also is going up. It's pretty slight. It goes more to the right than it goes up, but that doesn't really matter because it just does that forever. So the pattern is it'll just keep going to the right and up forever. And so it'll go up to infinity as well. And so that'll be the range. And we already mentioned that this graph is a function, but you can tell by doing the vertical line test, right? So anywhere I draw a vertical line, it only ever crosses the graph once, and so it's a function. All right, let's move on to another problem. So here they kind of set up a chart for us. And what you'll notice about this chart is that they are choosing the y value. So here's a case where instead of picking x and then plugging that into the equation to get y, it's easier to go the other direction. pick the y value first, plug that into the equation, and let the equation tell you what x is equal to. And that's often the case if the equation is solved for x already, right? So this equation has x equals y squared plus 9. And so based on the way this is set up, it'll be easier to plug in a number for y and let the equation tell us what x is equal to. And we're really being forced to do it that way here. Now, some students will take this equation and say, well, I don't like that. I like to just kind of do everything the same way. I'd like to choose x every time. And so they solve it for y, but you got to be really careful about doing that. Like if you do that here, you subtract the 9 to the other side, then you take the square root. But remember, take the square root of both sides. Got to do plus or minus. So really, you get something like this, which is also not very, you don't want to be dealing with this either, right? And so it's just risky rearranging the equation to solve it for the other variable because of little things like that. Many students will forget the plus or minus. So my advice is leave the equation the way it's given to you and choose the number for the variable that will be easiest to choose for, right? In this case, it'll be easier to choose for y and then solve the equation for x. So we'll just start with this. We have -2, right? So we don't really get to choose this time. MathXL has chosen for us. So they chose y equals -2 for us. We're going to plug that into the equation and let the equation tell us the value for x. Right, and so we'll get -2 squared, which is +4. 4 plus 9 is going to give me 13. And so I get x is equal to 13 in that case. So I'll put 13 in the box here. I'll do one more, and then I'll pause the video and suggest you do the same and fill out the rest of the table, but I'll do one more. So let's do y equals 1, +1. So we'll get x equals 1 squared plus 9. That's going to be 1 plus 9, which is going to be 10. So x is equal to 10 in that case. That was for this one. So I suggest you could do the rest of the table. I'm not going to put all the work on the screen for it. I'm just going to write the answers down. But I would say pause the video, fill out the rest of this table, and then resume the video to see if you came up with the right numbers. All right, so here are the values that you should come up with for the other y coordinates that we were given. And so we fill out the table first. Each of these is a solution to the equation, which can be written as an ordered pair. So this is 13, -2. Now the thing to be careful about, notice what I did there, is even though I chose -2 and I got 13 from the equation, when I write the solution as an ordered pair, the order has to be x value first, y value second. So the most common mistake students will make in a situation like this where they're choosing the y values and getting x from the equation is they'll write the solutions backwards in their ordered pair. Because they're like, oh, well, I picked -2 and I got 13 as my answer, and so they'll plot this point. But that isn't how it works, right? No matter which one you're picking and which one you're getting from the equation, the ordered pair has to have the x value first and the y value second. And so this would be the proper way of writing that solution. So then we also have 10, -1, 9, 0, 10, 1, 13, 2. And we want to plot all 5 of these points because they are solutions to my equation. Right? And so I'll draw the Cartesian coordinate system. Let's see. Okay, yeah. So I'll need more room out this way. And just kind of based on the numbers I'm seeing here, the graph's not even going to exist over here, so I won't bother drawing that out. And this is x right here. And so we need to go up to 13 on the x-axis. So it starts at 9, and then it goes all the way to 13. So I'm going to go ahead and number these one at a time just to try to keep the spacing equal. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, that's 13. That's 10 right there, right? That's 12, 11, 10, and then this is 9. Okay. And then on the y-axis, the numbers don't get that large, right? They go from -2 up to +2. And so I don't really need to number too many on the y-axis. I'll just do 1 and 2, both positive and negative. And then I'll plot these points. So we have 13, +2, which would be right here. We have 10, +1. We have 0, 9. So I feel like that point's a little too high. Again, shouldn't be a straight line either. But now that I'm looking, like that point's a little bit above the 2. And I picked the wrong thing here. Erase. And then let's plot that again. Should be a little bit lower. Right, so it should look like that. And then we have 10 comma negative 1. So this is where it gets a little confusing, right? Because we have 10 comma positive 1, but then we also have 10 comma negative 1. And then 13 comma negative 2 is our first solution there. And so what you end up finding is a curve that's going around like this. And it's kind of a difficult one to graph because the points are a little bit confusing, and I'm having trouble drawing anyways. Okay. Oh, I really missed that point. I'll have to redraw the point just to make it look better. But yeah, it should look something like this. I'm just going to draw this point a little bit. You know, this is kind of a trick that I will use. That really wasn't very good. But just if you draw the line and your point's just a little bit off of the line, just make the point fatter and it'll touch the graph eventually, right? So I'm just going to make that point a little bit thicker. It reaches the graph, and that way I don't have to redraw anything. So, but it's really a sideways parabola. That's what this graph is. It's a sideways parabola. Okay, now domain and range. To find the domain, we ask ourselves, how far to the left does the graph go? How far to the right? The furthest to the left the graph goes is this point here, which is 9. That's the lowest x coordinate that you can have in this graph. So that's the lowest value x can equal. So that'll go first. How far to the right? Well, it goes forever to the right, so infinity. And that's my domain. For the range, it's how far down, how far up. How far down does the graph go? Well, if you look at this part of the graph, it's going to go down and to the right forever. So it's going to go down forever. So negative infinity. And this part of the graph is going to go up and to the right forever. So it goes up forever. So positive infinity for the range. So negative infinity to positive infinity. It goes down forever and also goes up forever. Even though it's mostly going to the right, it is going up and down on those two parts of the graph. And it does that forever, so negative infinity to infinity. Is this a function? The answer is no, which is why it was a little bit difficult to graph, and that's why these points were kind of hard to, make sense of. In fact, I've seen students where, when they get points like this, and I don't know if it's because of the order they find them in, but I will see students that do weird things like this. Like they'll connect the points like in a zigzag. But really the pattern is there's an arc here and there's an arc down here. There's no zigzag. There's no points in between like that. So the graph shouldn't be drawn in between, right? So if there's no solutions in between these 2 points, there shouldn't be a line drawn between them. And I maybe saw this once or twice, but sometimes you get these bizarre answers that just stick in your mind. You're like, wow, that student really had the wrong perception of that situation. And so it's really not a common mistake, but I have seen students who have done that. So I just wanted to point that out. But it's not a function, right? Vertical line test like this one here, when x is 13, y can equal positive 2 or negative 2. That's one x with two different y's. It's not a function, which is what made the equation difficult to work with. It's what made the graphing difficult to do. All right. All right, so why don't you try this one? So pause the video. I'm not going to work out all the details on this problem. I mean, I'm going to, but I'm not going to talk you through it. I'll just work it out off camera, if you will, while you do the same thing. And then you can resume the video. You'll see all the solutions there. The table will be filled in. The graph will be drawn, and the domain and range, and whether it's a function or not. So do the whole thing, right? Fill out the table, graph it, find the domain and range, and determine whether it's a function or not. And I will do the same thing off camera. And then when you resume, you'll be able to check your answers to see if you came up with the same answers. I don't know why my head always looks crooked on the camera for some reason. So here is the solution to this problem. So when you fill out the table, these are the numbers you should have come up with. I said I wasn't going to do any of the details, but I thought this one is kind of tricky, and some students do get the wrong answers on these. So you'll notice there's absolute value here in this equation. And many students will say, well, absolute value is always positive. I don't know if that's the rationale, or if they think like when you get to this point that negative times a negative makes this positive, but that's not actually what happens. So you have to apply the absolute value first, and then the negative sign gets applied. So when you take the absolute value of negative 2, you get positive 2. And then you take the negative of that. So the answer ends up being negative every time. So the answer is -2 here, -4 here, -2 again, -4 again. So that's why the answer comes out negative. So I thought I'd illustrate why that happens. Absolute value first. And because the absolute value will always be positive, when you apply the negative sign second, the answer will always be negative, with the one exception being 0, 0, right? And so you plot these as points. I didn't write out the ordered pairs, but that's 0, 0, -1, -2, -2, -4. And this one is not a straight line pattern, but there are straight lines in this graph. And absolute values may be the one exception where you will have straight lines in the graph, but the graph isn't just a straight line. It's a V shape, which has a straight line going in one direction one way, and then cutting back the other direction in the other way, and a pointy end where the two lines meet. But you do get a straight line in this direction and a straight line in this direction. And that is common, not common, that is the pattern that you get with absolute value equations. For the domain and range, how far to the left, how far to the right? It goes forever to the left, forever to the right. So the domain's -infinity to infinity. For the range, how far down? It goes forever down, but how far up? It stops at 0, right? There is a highest point on the graph, which is 0. That's the highest value you can get for y. And so that would be the upper bound for the range would be 0. And is this a function? Yes, right? Passes the vertical line test. It's a function. All right, we have 2 more topics to talk about in this section. The next one is piecewise functions. So a piecewise function is a graph in which 2 different equations are cut in 2 and put together side by side as a graph, right? And so here's an example of what a piecewise function looks like. In class, I don't always do this because it takes a little bit of a setup, printing out a couple of graphs and getting some scissors, which I don't always have access to because I don't really need scissors most of the time. But literally, a piecewise function is taking the taking the graphs of 2 different equations, cutting them along the same vertical axis, x equals 2 or x equals 5, whatever, wherever you want to, tape them together, and taking the left half of one graph and taping it to the right half of the other. As long as you're cutting along the same vertical value of x, that works. That is exactly what a piecewise function is. Taking 2 different graphs, cutting them along the same x value, and taking the left half of one and gluing it, taping it to the right half of the other. And there you have a piecewise function. So that's exactly what's going on here. We have one line that's going in this direction, and we cut it off at x equals -1, right? So at -1 here, we stop drawing this particular line, and we switch to drawing a different line. And so we have a different equation, different graph, once we hit x equals -1. And so I have the right half of this line taped together with the left half of this line. So for this particular variant of the problem, we've been given the graph, and what we want to do is construct the equation that describes this graph. But to describe this graph as an equation, I have to describe the equation that gives you this particular line, the equation that gives you this particular line, and when each graph is getting used. The left half of this one, the right half of this one. All of that information has to get packaged into an equation to describe the graph that you see on the screen right now. The first thing you want to look for is where you're making the switch from one graph to the other, which we've already identified as being at x equals -1. So I usually will draw a vertical line through that, and I have a straight line tool for this software, but I like to draw it as a dotted line, and it doesn't have that capability as far as I know. So I'm going to try to draw it by hand is what I'm trying to say. I don't know if you can even see that, but so there's my vertical line where the graph is changing from one to the other. And as I mentioned, this is passing through -1 on the x-axis. So the way you would describe that vertical line is by that value of x. This is where x is equal to -1. That's where we switch from one graph to the other. To the left of that vertical line is where the x values are smaller than -1, right? Because if you think of the x-axis as a real number line, the numbers are smaller to the left, they're larger to the right. So the vertical line is where x equals -1. To the left of that is where the x coordinates are smaller than -1. And to the right of it are where the x coordinates are bigger than -1. And that's actually going to be relevant when we put all of this together. So I want to find the equation that describes this graph in this region over here where x is greater than -1. To find this equation, we're going to have to use something we learned back in chapter 1. And I have to admit, I will often feel disappointed when I get to this problem in college algebra and I say we have to find the equation of this line, and a lot of my students act like they've never done it before. And it drives me crazy because we did that kind of problem back in chapter 1. And I know we did a lot of stuff in chapter 1, but this is something you've done in other math classes, not just in college algebra. You've done this before. And at some point, you're going to have to retain the information for the topics that you've done before in order to, build, to go on to more interesting, complex math problems. You have to be able to bring along that information from problems that you've learned previously. And so that's where we're at right now, right? The topic here is piecewise functions, which is a different concept. But within that concept, we have the idea of graphing lines and finding the equations of lines. And that's something that we've learned before. And so in order to do the piecewise functions, you have to be able to bring that information from before. And it's just going to get worse. I'm just going to warn you now that as we go through the next few chapters, the material we cover relies on previous material that we've discussed. It gets especially bad in chapter 4 because a lot of the topics in chapter 4, which are on exponential and logarithmic functions, utilize concepts from chapter 2. And so if you aren't learning the material in chapter 2, or if you're not retaining that information, when you see it again in chapter 4 being used in, for those new functions that we're going to learn in chapter 4, you're really going to struggle. So it's really important. I maybe should have mentioned this in chapter 1, but when you're learning this material, don't learn it for the moment and think, I just got to get through this test and then it doesn't matter anymore. That's not how this course is designed. It's hierarchical. You need to retain the information from previous sections in order to be successful in later sections. Right? So how do we find the equation of a line? You need 2 points to do that, right? So this is a line, and as soon as you know it's a line, you should think y equals mx plus b, right? That's the formula for the equation of a line. To get started finding that equation, the first thing I need to find is the slope. And so this gets back to the first thing I just said, which is we need 2 points. We need 2 points to find the slope, right? Because we know the formula for the slope is y2 minus y1 over x2 minus x1. And to, get that, either that, or I guess maybe the easier way here would be to count, right? Rise over run would be another way to think of this. And so if you could think of this as rise over run, right? And that's actually probably easier since we have the graph to look at here. So, but either way, whether you're going to use this formula or the concept of rise over run, you have to have 2 points marked. And from those 2 points, you can figure out the slope. So they've marked 2 points for us here, right? We have, let me use a different color. We have this point here, and we have this point here. Right? Those are 2 points on this line that we're trying to find the equation of. And so using those 2 points, we can measure the rise over the run. The rise is the vertical change. The run is the horizontal change. So going from this point here to this point here, we're starting at -3, right? That's the y coordinate for that point. So that's how low we are. We're going up to 1 on the y-axis. So what's the vertical change there? It's 4. It's going up 4, so it's positive 4. So that's going to be my rise. The run, we're going from -1 on the x-axis, right? That's where this point's located, over to 3 on the x-axis. So from here, drawing this really funny, from here to here, it's going from -1. That's the x coordinate. I'm a little bit too far over, but from like right here to the right, it's going from -1 to 3. That is also a change of 4. And since it's going to the right, it's also positive 4. And so the rise is 4 and the run is also 4. 4 divided by 4 gives me a slope of 1. All right, and so the slope is going to be 1. B is the y-intercept, which sometimes you have to calculate, but when you're given the graph, you might be able to just see it in the graph, right? So the y-intercept here, if you look, is at -1. That's my value for B. And so B is -1 here. So I get y equals x minus 1 when you simplify that. That's the equation for the line on the right-hand side of this piecewise function. We also need to find the equation of the line that's on the left-hand side, using a similar method, right? And so I've made a big mess of things here. I think what I'd like to do is erase what we've already done. Because, in the recording, if you need to see this information again, you can always rewind it back to this. But let's go ahead and erase this. So this was all the stuff we did to find the equation of the line on the right-hand side. Now let's do the same thing for the left-hand side. We need 2 points. Again, it's a line, going through the same reasoning. This graph is a straight line. For a straight line, the equation should fit the form y equals mx plus b. To find m, we need to use 2 points. We have these 2 points marked here. What's the rise over run here? Excuse me. We're starting at this point here, which is at 4 on the y-axis, right? That's the y-coordinate. And it's dropping down to 1. And so what's the rise there? We're going from 4 down to 1. That's a change of -3. Right? It's negative because it's dropping down 3. That's why it's negative, right? And then for the run, it's going to go from -4 to to -1, right? Because it's over here on the left-hand side. So from -4 to -1, that's a change of 3. It'll be positive this time because we're going to the right. And so the slope, if we think of it as rise over run, is going to be -3 because it goes down 3 and then to the right 3. And so we get a slope of -1, which they're trying to be nice here, right? They're trying to give us numbers where the slope works out very simply. But sometimes, especially like with the number 1, it's maybe almost too simple. So it makes it kind of awkward to deal with. But that's the slope, -1. Now for B, the y-intercept, we run into a little bit of an issue here because the line actually doesn't ever cross the y-axis. It gets cut off before it makes it that far. But the value for B is still going to be the number where the graph would have crossed the y-axis if it were allowed to continue. Now, if you can't tell from the graph you were given where it would end up crossing the y-axis, you can calculate it. Just put plus B here, take one of your points like this one, -4, 4, and plug that in for x and y, and then you can solve for B. Right? So I'm going to plug in 4 for y, plug in -4 for x, and then I can solve for b. I'll get 4 equals 4 plus b, subtract 4 from both sides. You get b is equal to 0, which you might be able to tell by just projecting, right? If the line were to continue, where does it look like it would cross the y-axis? It looks like it would cross right here, right at the origin, which is 0. Right? So the y-axis would be 0. Sorry, the y-intercept would be 0. It crosses the y-axis at the number 0. And so b is going to be 0, so we can plug that in. So we get the equation y equals just -x, right? Because we're going to plug in 0 for b. -1 times x is just -x. And that's going to be the equation of the line on the left-hand side. Now, that's a mess. Look at this screen, right? There was a lot of work that had to be done. We want to take all of that information and package it in a nice, neat, efficient way that's easy to read. So here's how we end up putting all this information together. Right. So to write the equation of this entire piecewise function, we're going to write both of these equations. We have y equals x minus 1, and we have y equals -x. Right. And then we're going to specify when each equation is getting used. We use y equals x minus 1 when x is greater than -1. Right. What you might want to say is, oh, you use y equals x minus 1 on the right-hand side. But we have to be more specific than that. And we want to be able to describe that in an easy way that we can contain within the equation. So a good way of describing this region on the right is by this. Right? This is the region where x is greater than -1. And when in that region, we want to use this equation. All right, so we're using this equation in this region where x is greater than -1. So use this equation when x is greater than -1. We will use the other equation, y equals -x, in this region over here where x is less than -1. All right. There's a couple more things we have to do here. So one thing we're going to do, just to make it a little nicer looking, is instead of writing y equals twice, that's redundant. We don't need to write y equals both times. We'll merge those together and just write it one time as y equals, and it can either equal x minus 1 if you're in this region, or it will equal -x if you're in this region. And to kind of, bring those two equations together into a single equation, we will use a big curly brace. So this is the way piecewise functions are written, right? And then because it's a function, because it passes the vertical line test and we're calling them functions, right? Piecewise functions. Instead of using y here, I'm going to use f of x, right? But remember, that's just the y variable. And the last detail we have to figure out is, what about when x equals -1, right? I didn't address that here. Right, sorry, that was kind of weird. I don't know why I wrote all those stray marks there. Well, let's try that one more time. What about when x is equal to -1? Because here we have when x is bigger than -1, use this equation. When x is smaller than -1, use this equation. But what about when it's equal to -1? Which equation should we be using? And the way you will know which one to use is by looking at the graph, the endpoints on these two graphs, and seeing where the open circle is versus where the closed circle is. Now, I've made a lot of marks on here, so again, I will erase so we can get a better view of the graph. And I'm just going to kind of erase all that stuff too. Maybe I'll just erase that also. Okay. So here we have an open circle on this endpoint here. Here we have a closed circle. So it's just like with inequalities, the way you learned inequalities, right? If you don't want to include the point, it's an open circle. If you do want to include the point, it's a closed circle. So here, for this graph, this point is being included, which is on the line where x is equal to -1. So on this line where x is -1, this point is being included. And it's being included with the graph on the right-hand side. This point is not included because it's an open circle. So for the graph on the left, that point that's on x equals -1 is not actually being included as part of the graph. It's being left out. And the reason we have to be careful about that is if we included both points, it would no longer be a function, right? Because here's a vertical line, and if both points were part of the graph, it would cross the graph in two different places. It would not be a function at that point. So we can only keep one of these points for it to still be a function. In this situation, it was decided to keep the point for the graph on the right-hand side. So that's where we want to put the equals. When x is equal to -1, we're using the graph on the right-hand side, so we'll put the equal sign underneath that condition. And when x is less than -1, we use this equation, but not when it's equal to. When it's equal to, we use this equation, right? And so this is what the equation for a piecewise function looks like. Now, this is really the more difficult version of this problem. So for piecewise functions, there's two variants. There's the variant where you're given the graph and you have to construct the equation. That's the hard one. The easier one is they give you the equation and you figure out the graph. I started with this one though because I want you to see why the equation looks the way it does, right? So this was the most efficient way that we could take all this information and package it together. And that's why all of this stuff is here. That's why there's two different equations. That's why there's these conditions being indicated over here, because of everything that's going on in the graph. So now when I show you the other variant, which is going to be the first one you'll see on the homework, the easier variant, you'll understand. You won't panic right away and say, oh, wow, what's going on here? There's crazy symbols and whatnot. You now understand why it has to look that way. There are two different equations that are being graphed, and we have to describe what those equations are and when they're getting used, where we're putting each graph, right? And that's what all this information is for. Now, I like to use the word when here, when x is greater than 1, but I don't know. This textbook uses for. I think for is actually probably the more common thing to put. But it means the same thing, right? Use this equation. So again, there's two equations here. We have f of x equals x plus 1. We use that equation in the region where x is greater than 1. And there's another equation, f of x equals x minus 3. We use that equation when x is greater than or equal to 1. Sorry, I said the wrong thing. Sorry about that. We use the bottom equation when x is less than or equal to 1. I don't know why I said greater than. I just kind of blinked out there. Okay. The point I wanted to make was, when are we switching from one equation to the other? Most students are pretty good at picking this out. It's at x equals 1. Right? This is where we want to switch from one graph to the other graph. So the first thing I do when I'm asked to graph a piecewise function is I identify where will I be changing from one graph to the other, and I mark that on my graph first. All right, so here's the Cartesian coordinate system. Where is x equal to 1? Here's 1 on the x-axis, but where is it x equal to 1? It's the entire vertical line that crosses through 1 on the x-axis. So when I say x equals 1, I mean this entire vertical line here. This is where x is equal to 1. And that's going to be my boundary. That's the boundary between the two different graphs. So the graph on the left-hand side of this boundary, whatever ends up being over here, cannot cross this boundary. It gets cut off at this line. And once we cross this line to the other side, there's going to be a different graph over here, a whole different graph, right? A whole different line. And the graph that's on the right-hand side cannot cross this boundary over to the left-hand side. So this really effectively cuts off the two graphs from one another, right? They're stuck in their own worlds, if you will. Now, what is this region to the left of this vertical line? What's a good way to describe it? If this is where x is equal to 1, then to the left is where x is less than 1. That's the way you would describe that region. And to the right is where x is greater than 1. So what do I want to graph over here where x is less than 1? I want to graph the red equation. I want to graph y equals, again, f of x, it's just y. I want to graph y equals x minus 3 over here. And then I want to graph y equals x plus 1 on the right-hand side where x is greater than 1, right? Because that's what it says. When x is greater than 1, use this equation. Here's where x is greater than 1. I will use this equation in this region. When x is less than 1, use this equation. Use x minus 3. So here's where x is less than 1. I will use this equation. So how do I graph these lines? The quickest way to do this is to use the y-intercept, right? So the y-intercept here is 0, negative 3. And the slope, which is 1, which you can think of as 1 over 1, which means I'm going to go up 1 and to the right 1. But where do I do that from? I start with this point here. So we're going to start at 0, negative 3, which is down here. Mark that point first. That's the y-intercept. From there, I'll use the slope as a set of directions to help me find another point. So from here, I'm going to go up 1 to the right 1. And I end up right on the boundary, which I'm marking as a circle, but I got to be careful on the boundary, right? Because one point will get included, the other point won't. And so I don't know if I want to bubble that in yet. I need to think about that first, and I'm not ready to think about that just yet. So I'll just kind of mark it with an X for now. There's a point here, but I don't know if it'll be open circle or closed circle yet. But it's fine. You might say, well, should we avoid that boundary? No, because the graph needs to reach that boundary. So we kind of want to know where it's going to land on the boundary, but we don't know if we should use an open circle or closed circle yet. But now we have these 2 points, and with those 2 points, we connect them with a straight line. And now we have the graph on the left-hand side. Let's do the same thing on the right-hand side, except that we can't quite do it the same way, right? The y-intercept here is 0, 1. I kind of wrote that funny, but why is that a problem? Because that point is located right here on the other side of the boundary, right? I can't cross that boundary to plot this point for this equation. This equation has to stay over here on the right-hand side. So that point is off limits. It's cut off from that point. So I can't use that to help me graph this equation. So I can't use the y-intercept. So what I need to do instead, because remember, to graph a line, you just need 2 points. The limitation is I need 2 points that will be in this region over here. I can't use any points on the left-hand side. So I'll just find 2 points using the generic method we talked about earlier, picking a number for x, plugging it into the equation, and getting a value for y. And I'll do that twice to give me 2 points. But I have to pick values of x that fit this description. They have to be bigger than 1. So for example, 2 would be fine. Right, so here's x equals 2 right here. I'll plug that into the equation. I'll get 2 plus 1, which is 3. I'll get y is equal to 3. All right, so go ahead and mark that point here. There's 2 comma 3. And I need one more point to graph this line over here. I'll pick 3 for x. I'll plug that into the equation. 3 plus 1 is going to give me 4 for y. And then that gives me another point that I can graph. All right, so here's 3 comma 4. All right, and now I have 2 points. I can connect them with a straight line, and there's my graph on the right-hand side. Except that, remember, I mentioned that the graph needs to fill in the entire area that it exists in. I don't know, I'm not saying that very well. The graph needs to occupy the entire region that it exists in. Right? So if I start at this point, which is the first point I found, and I draw a straight line connecting it to the other point and extend it to the right, that's great. It should do that. But it also should extend back to the left as far as the boundary for that region. So what I'm saying is you don't want to leave this gap right here. This graph needs to fill in all the way to the boundary. So I need to draw the line back towards the boundary, and wherever it strikes the boundary, I'll wait because I have to decide if it's open circle or closed circle. But the graph needs to go not only to the right forever, but also back to the boundary. And so just make sure you don't leave any gaps like that. And so we draw it back this way, and then it hits the boundary here at 2, right? That's kind of where it's going to land on the boundary. Now, where do I use open circle and closed circle? That depends on where the equal sign is in the equation. So the equal sign for these conditions is located here with the bottom equation, which means that's the equation you want to use the closed circle on for the endpoint. And that's the equation on the left-hand side, right? This is where x is less than 1. That's where the equals to is located. That means this endpoint should be a closed circle, which means the other graph, the endpoint should be an open circle. And that way it maintains the property of a function. Now here's a vertical line that still only crosses the graph once. It doesn't cross it here because that point is not being included. It only crosses it here. And so that is what the graph of this piecewise function should look like. And there's a gap here. Now it's asking for the domain and range. So the domain, remember, is how far to the left, how far to the right. This is the same as it was for the previous problems that we've done. It goes forever to the left, so negative infinity, and it goes forever to the right. And so the domain is negative infinity to infinity. What about the range? The range is how far down the graph goes and how far up it goes. Now, if you're thinking about the range, how far down, how far up, you might say, well, same thing, right? Goes down forever, goes up forever. But that doesn't really capture the full picture, right? It does go down forever. It does go up forever. But there is a gap here in the middle. And that gap does not affect the x-coordinates, right? No x-coordinate is left out. We have -1 somewhere on the graph. We have 0. We have +1. We have x equals 2, x equals 3. Every value of x is accounted for and exists somewhere on this graph. So the domain is all real numbers. There's no missing x values, but there are missing y coordinates. For example, -1 as a y coordinate does not exist on this graph. Y does not equal -1 for this piecewise function. It just doesn't exist anywhere on the graph. And so it shouldn't be in the range. So when we do domain and range, we have to take into account any gaps there are in values. So when I say, oh, it's just how far down, how far up, that's an oversimplification, which normally works fine. But you have to take into account if there's any missing values in between as well. So the way I kind of think of it is, how far down does the graph go? Go ahead and start with that. That's negative infinity. Then from there, you're starting from the bottom and you're working your way up. So from negative infinity, as I head back up through the graph, does it stop at any point? And the answer is yes. It stops here temporarily at -2, right? That's -2 on the y-axis. It stops there and it includes it, right? It's a closed circle. So we use a bracket on the -2 because that value is part of the graph. It stops there temporarily, and the graph doesn't resume again until we hit positive 2 on the y-axis. So we have this gap here of y values, -1, 0, 1, and the graph doesn't resume again until we reach 2, but it doesn't really include that number because we have an open circle on that point. So I'm going to put 2 here because that's where the graph starts up again, but parentheses on the 2 because it's not actually included in the graph. And then from there, it goes up forever, right? So it starts at -infinity, stops at -2, right? We have a graph through here. Then we have a gap, and then the graph doesn't start up again until positive 2. And so that takes into account the gap in the y coordinates that we see in this graph. And then we use a union to connect those two intervals. And so that would be the range. And probably one of the more difficult things to do with this material. Now, on the homework, the graphing is multiple choice. I intentionally left it off because I really don't like multiple choice questions in math. But on the homework, it'll be multiple choice. And for my exams, I usually just print up an exam from Math Excel. So your exams will be on paper. You already know this because you would have taken the Chapter 1 test already. But I leave the multiple choice on there. But the domain and range are not multiple choice. So when I'm grading this problem, I don't put as much weight on the graphing part because it is multiple choice, and I put more weight on the domain and range since you have to actually know what you're doing to figure out those answers. And so the domain and range will count for more than it normally would on this problem on the test because of the multiple choice nature of the graphing part. Anyways, one more topic. So I'm sorry this video is already over an hour long, but this is a pretty quick topic, so we should be done in like the next 10 or 15 minutes, hopefully. A graph is increasing if it is going up. That makes sense, right? I mean, the graph is increasing if it's going up. The graph is decreasing if it's going down. But there's a little bit more to the story than that. As it moves from left to right, it's really important that we agree on that direction when we're making our assessment as to whether a graph is increasing or decreasing. If we don't have that agreement, then you might wonder how that would be possible, but I'll show you in just a second. We might disagree on the description that a graph should have if we don't agree that we're considering whether the graph is going up or down as it moves from left to right. If we don't specify that, we can describe the same part of the graph with different labels, where I would say it's increasing, whereas you might say it's decreasing, if we don't have this agreement, right? So the graph is increasing if it's going up, it's decreasing if it's going down, it's constant, the graph is constant if it just stays flat. But in every case, we have to consider the direction as the graph goes from left to right in order to get the correct label on that part of the graph. So here's an example where students who aren't careful will get it wrong. So it's a parabola, right? Now, you might look at this graph and say, it's going up right here, and it's going up right here, right? Because if you're starting from the middle and you look to the right, it's going up. So you might say, oh, this is increasing. And from the middle and go to the left, it's also going up. And so you would say it's increasing here. I get students that do this on the test. And that is incorrect. That is the wrong description. Somebody else will look at the same graph. I wish I should have copied and pasted it. I'll try to reproduce it over here. Somebody else can look at the same. Oh, I did a really bad job already. Somebody else can look at the same graph, just pretend that's the same, and say, well, if I start over here, and this is supposed to be like your eyeball. If I start over here and I look to the right, the graph is going down here, right? It's dropping. So I would say this is decreasing. And then once I reach this point here, it starts heading back up. So then it's increasing. This is actually the correct description based on the way we're defining it. You have to always be moving from left to right, which means when you look at these graphs, you don't want to start in the middle. You don't want to start in the center of the graph. You have to draw your attention, your eyeballs, to the left side of the graph. You have to start from the left-hand side and move to the right. That way you're always going from left to right. Start from the very left-hand side and scan to the right. And based on that direction, you can decide whether it's increasing or decreasing. And that way we're all coming up with the same description. Because if we're all going to start on the left-hand side and look to the right, we'll all say this is decreasing. We will all say this is increasing. So we are on the same page. All right. So this is decreasing here. This is increasing here. All right. So don't look at it like that. You have to start from the left-hand side, the very left-hand side of the graph, and look to the right and see if it's going up or down from that angle. All right. Now, how do we describe it? Now, here I'm just kind of pointing to it. It's decreasing here, it's increasing here, and just pointing at the graph. But what if I needed to type that up in an email to somebody to say, for this equation, here's where it's increasing, here's where it's decreasing, and I can't physically point to the graph itself? How would I describe the regions where it's increasing and decreasing? You want to use the x coordinates. So I didn't really label this very well, but let's look at an example from the homework. I guess I have it written right here. Describe where the graph is increasing, decreasing, or constant as intervals of x values. All right. So let's take a look at this example from the homework, where we actually have some x values to look at. So here, again, if we're not in agreement, many students will look at this graph and start at the middle because that's just naturally where your eyeballs are drawn. Right? This is there's a term for it in art, which is like the center of focus. I think that's the name of it. And so when you're drawing a painting, you will design it with a certain center of focus so that when somebody looks at your painting, you're kind of controlling what they look at first and where their eyes are going to go from there. That's an artist's technique. Now with math, we're not doing anything like that intentionally, but it's human nature to look at something like this and go instantly for where there's the most interesting thing, which is the middle, right? This is where it's most interesting, but that's not where you want to start making your diagnosis on where this is increasing and decreasing. You have to break your focus on the interesting middle part here and bring your eyeballs to the left-hand side of the graph. You want to start here and look to the right. And as I go from the very left-hand side to the right, the graph is going up. It's going up. Starting from this point here, it goes up. So here is where it's increasing. Once it reaches that interesting point here in the middle, it starts heading back down. So there is where it's decreasing. And this graph is never constant. There's no constant part to this graph. It's increasing here, it's decreasing here, and that's it. So how do I describe this region where it's increasing? Well, where does the graph begin? It begins at -1. For x, right? So you want to use the x values to describe where the graph is increasing. It starts increasing at x equals -1. So make sure you look at the x value. So starting at -1, and it continues to increase until we reach x equals +1, right? This point is where x is equal to +1. So it's increasing from -1 to +1. That's this region here. Those are the x values for this particular region. And then it's decreasing starting at 1. And it continues to decrease to the end of the graph, which occurs at x equals 3. So make sure you're using the x coordinates to make those descriptions, not the y coordinates. You want to use the x values where it starts increasing and decreasing. All right. And so this would be your answer here. And you would say it's never constant, because I think it will ask you that. It'll say, where is it constant? You'll just say, this graph is never constant. All right, so why don't you pause the video for a moment and see if you can identify for this graph, where is it increasing? Where is it decreasing? Where is it constant? Describing it using the x coordinates. Okay, so what you should have come up with for that problem is that it's increasing. So again, you start from the left-hand side of the graph over here. So bring your eyeballs over here. As you look to the right, the graph is going up, right? So when you start from the very left-hand side and start looking towards the right, the graph is heading up. So it's increasing here. And this one isn't like this graph here where there's a beginning point. There's an arrow here, which means it goes down and to the left forever. So when you're starting from the very left-hand side, you're starting from negative infinity. So from negative infinity until x equals -1, that's where it stops increasing. So negative infinity to -1, the graph is increasing. Then it's flat, which means it's constant from x equals -1 to x equals +1. That's where it's constant. and then the graph just terminates. It just ends right there. And at no point does this graph ever decrease. This is a strictly either increasing or constant graph. It never decreases. It never goes back down. And so when Math Excel asks you, where is it decreasing, you would say never in this case. Sorry about that noise. That was my mouse. All right, last example and we're done. So again, I'm sorry for the length of this video. Determine the correct graph that best depicts the following scenario. Profits for a company fell during the 50s and went flat after they crashed in the 60s. The company saw a period of moderate decline in the 70s. So the profits fell, went flat after a crash, and then declined some more. So this company is not doing good, right? It's just dropping. So this, it looks like a word problem, but I really would not go that far in describing this problem. It's giving you a scenario, and really it's all about identifying where is it increasing, where is it decreasing, where is it constant. All right, so if the profits fell during the 50s, if the profits are falling, the graph should be doing what? The graph should be decreasing if the graph is indicating the profits for that company for that period. Then it goes flat, which means the graph should be constant. After a crash, so maybe we'll be able to identify what that looks like in the graph in just a second, but what I'm looking for so far is a graph that's decreasing at first, then constant, and then a period of moderate decline, which means it starts decreasing again. And at no point is it ever increasing. So I'm looking for a graph that decreases, is constant, and then decreases again. So which of these graphs appear to exhibit that pattern? It's graph A, right? Graph B is increasing at first, right? It's going up as we go to the right. That doesn't fit this description. This one is decreasing, jumping back up, decreasing. So this one's just decreasing every time, but it has these like discontinuous jumps back up, which I don't know what would be happening at the company for that to happen. Maybe buyouts, or I don't know what it could be, but something that just causes the profits to jump in some unexpected way, but then drop again. Jump in an unexpected way, drop again. That's not happening here. Here we have decrease. We have some turbulence here where it's kind of flat, but then there's an increase. But this problem never describes the company having any kind of increases. This is the graph that fits the description. It's decreasing. There's a crash, right? That's kind of what the crash looks like there. Then it's flat, right? Constant, and then decline, right? So A is the graph that fits that description. All right. So that concludes the video on section 2.2. I'll see you in the next video for section 2.3.